All right, well, it's great to see you guys all here. We're here to present the Private Proof API. We've been working on this for a long time, and oh yeah, no worries, Victor. I just hope that we're not like jumping ahead. Yeah, but okay. So we've been working on this for a long time. We're thinking really about anti-fraud use cases and anti-abuse use cases, and we're going to describe it on a technical basis to you guys today, and hopefully, trying to figure out why we're muted. Okay, great. You guys can hear us though. Okay, perfect. Okay, so essentially, yeah, we're going to go through this. All right, do you mind going to the next slide? Awesome. So the primary use case that we're really considering, we've talked a lot about in the anti-fraud community group, is that spammers tend to clear their state in an attempt to look like a new user. And essentially, this can cause all sorts of different types of fraud. And people have developed different ways, like some using shared storage, some using, cookies or other third-party storage. And people are trying to figure out new clients versus old clients, and maybe put newer clients through some different types of verification or authentication. And to do this, we use zero-knowledge proofs, which is a broad and old area of cryptography that hasn't necessarily seen. Oh, can you go to the next slide, Ari? Sorry. Hasn't necessarily seen like a huge amount of applications, but now increasingly like more and more applications. So I wanted to give a little bit of a primer on that technology and how we're thinking about our specific use case, and kind of give you a vague idea. And then we'll go through the API, and Ari will tell you exactly how we're intending to use this. So next slide. So zero-knowledge proofs involve a secret, some data that you have in your local storage that you're never going to reveal to anybody, and a verifier that wants to know something about that secret. And we are in the prover in particular. And for instance, we can have a digital signature that we were issued by some issuer upon being authenticated in the past. The verifier wants to ensure that indeed we were authenticated in the past, in particular that we possess a digital signature. And so we prove to the verifier that there exists such a signature signed by the issuer's public key without revealing anything about the digital signature itself. And the way that we do this is with a technology called zero-knowledge proofs. And this is what zero-knowledge proofs are, is this ability to prove something about data that you hold and that you don't want to reveal, at least in full, to a relying party or a verifier. Can you go to the next slide? We can prove lots of things with zero-knowledge proofs. Like we could prove a possession of a digital signature or a message authentication code, which is like a single-party version of a digital signature. We can also prove that a secret number X is less than or equal to a given public bound Y. We call this a range proof. And in fact, everything can be proven. Anything that can be proven, or any program that can be written, can be proven. The execution of that program can be proven in zero knowledge using a variety of tricks, but these tricks are not always so efficient. And so in general, we look to optimize and find specific or smaller instances that we want to prove. And so we're going to talk about our specific use cases today. Next slide. So anonymous credentials are a body of literature that exists about building these types of signatures that you hold in your possession and you don't reveal in full, but you prove various aspects about. We use techniques such as digital signatures or MACs, like I said before, but instead of showing the signature or MAC, we prove aspects of them in zero knowledge, like I've said before. And these technologies allow us to gain access to resources, enforce policies, and perform arbitrary authentication or authorization logic while maintaining users' privacy maximally in that environment. So like only revealing the information that is required to do that authentication or authorization query. Next slide. But there's kind of a problem with what I've said so far, in that because we don't share our credential with the relying party, we can create an arbitrary number of proofs from that credential and distribute them amongst a huge army of bots. We could even distribute our credential and they could locally create proofs of an arbitrary amount, and then they could just authenticate to everything. And there's sort of no point of this at the end of the day. And so that problem would be solved if we could limit the number of valid proofs that could then be produced given any given time period. We call this rate limiting. And it's critical to deployments of anonymous credentials in practice. You might hear this referred to as like pseudonyms, which is that you might have only a rate limit of 1 in a given context, and you reuse that anonymous credential, and you could think of it as like identifying you only within that context as well. You go to the next slide. So previously we would have signed a digital signature. Now we have a partially blind signature protocol. The issuer sees the contents of the credential, for instance, some aspects about the user, but they also sign a hidden value, like they can't see this value, but it's a pseudo-random function seed. And then within a given context, the user will evaluate that pseudo-random function on a well-known context. For instance, for us, the context is the epoch, so the epoch of time in which you're having a certain number of invocations of your credential, and a counter, where the counter ranges from 0 up to the rate limit -1 to get a token T, the rate limiting token. And then they prove that they have a digital signature of the credential and the PRF seed, and that they prove that the T value, which is random, so you can reveal T to the relying party, you prove that it was computed correctly on the context and the counter. Then we use a range proof to show that the counter is within 0 to rate limit -1. And this means that we can only produce up to valid rate limiting tokens that are unique in any given epoch. So it allows us to rate limit arbitrarily within any context, but in our case, within each epoch of time. So like, from 5 p.m. to 9 p.m. or something like this. Yeah. And I'll give it away to Ari to talk about the web API.
Okay, so there is an explainer, which the link is shared later on, that has more detailed view, but I'm going to try to give an overview of the actual web API we're proposing to use what Sam just discussed. So first, I want to talk about what we're trying to achieve, right? So we're trying to reduce the challenge friction for users who are likely to be benign, right? And to have a function that's giving off a low amount of bits for what we're about to discuss, basically 1 bit of information to be able to validate that, right? Not the user's exact identity, but some information you're verifying about them. This information should be clearable, and it should be able to run on sort of arbitrary user devices. We aren't trying to increase friction for users who aren't able to support this system for some reason or have it disabled. We're not trying to better enable cross-site tracking, and there is no reason that this score can't be cleared. It's not being it's not like tied to the device in some way. It could be shared between browsers potentially. And that's why Sam went over the mechanisms for trying to sort of reduce the value of sharing it between browsers specifically for the purpose of generating multiple tokens. So what is the overall flow? Right, so the browser at some point will have a reason that it wants to get a token from some issuer. This is likely because you visited some website and maybe it's providing a CAPTCHA to you, and it wants to, you completed the CAPTCHA and it wants to generate this token to store it for the future to be able to note that you did that. So it generates a request, it sends that to the issuer, who validates that and then sends back a signed token that the browser then receives and stores for later use. So after that, some time passes, and then the user will end up visiting a site again that wants to check what the state of the token that was previously stored was, perhaps to bypass a challenge or to be able to do something else to reduce friction for the user. And so the issuer decides they want to have this check occur. They add it to the JavaScript of whatever page they're sending. The browser sees that, is able to generate a proof, send it back to the issuer. The issuer can validate it and then take whatever action it decides to based on whether or not the token validated successfully. So the proposed API has a few key parts. So first, in terms of public information that's shared, any site that wants to use this has to distribute a public key that's used to validate the tokens that are sent. This is so the browser can verify that the token they got is actually valid. There needs to be information about the epoch, specifically how long it is and what the sort of rate limit of tokens you want to be able to generate per epoch is, because that's key in being able to, for the browser to be able to generate proofs. So this information could go in a well-known file, or it could otherwise be registered somehow so the browser is able to get it at the time that an issuer decides that it wants a token to be stored on the browser. So then for the flow itself, right, the user agent has to have an ability to request a token through a JavaScript API. The server is going to generate that token. The user agent is going to store it. This is the flow we just went through on the previous slide. And then for the proof flow, similarly, the agent has a JavaScript API to trigger the generation of a proof based on a previously stored token and to check it against some information that the issuer is providing. That would then be sent back to the server for validation. And then the response to that is going to end up being a JSON blob, which the browser, when it gets back, could use to set some data, set a cookie or set some local storage or take some other action based on what was gotten back. And then we want to integrate into existing data clearing UX and APIs. So let's get to a more specific example. So in this case, the server wants to check if the user agent has completed a captcha more than 1 day ago. Right? The idea here is that if this isn't a new user and they've already successfully completed a challenge, then maybe we have some better assurance that this user doesn't need to be re-challenged. So if we look at the client-side code, you'll see that it gets the private proof manager. It checks to see if they have a token. If they already have a token, then they're able to generate a proof, right? So it gets to the constant for it sets up a constant for what 1 day ago would be, and then it attempts to generate a proof and send it back to itself for a comparison of the token to 1 day ago. With the UUID here is used as part of the rate limiting information, and then whatever it gets back, it's able to set data from that proof. It could be cookies or some other data in order to make a decision about continuing, right? If the proof successfully passed, then maybe we can bypass a challenge and no further actions needed. Otherwise, if the challenge couldn't be bypassed or if a token wasn't set, then we're going to run a challenge, set some data based on that challenge, right, to validate this context to move forward in whatever flow it was a part of, be it like a purchase or maybe liking a comment on social media or something else. And if the challenge was passed, then it could make sense to request a token. You'll note here that it checks if it already has a token. It's important to do that, right, because there's a window where a token has already been set, but it hasn't matured, right? In this case, the token is storing a current timestamp, and the proof that's generated is checking that timestamp against what 1 day ago is, right? So there's a window of 1 day between when a token could be set, but might not be yet generating valid proofs because it isn't quite old enough. So we want to make sure we don't override the token in that window before it matures into usefulness. So there are a lot of considerations here, right? We're concerned about ways that the user could be identified through this, or ways that it could add additional cross-site tracking bits, or like side channels if the different sites are able to check whether or not different rate limits have been hit, or the sites are able to check whether or not a token has been set and use that as some kind of a communication channel. We want to make sure that ideally the token and the proofs that are generated aren't shared with the renderer in case the renderer has been somehow compromised. You want to be able to trace the generation of proofs for debugging in dev tools. And so we've tried to address each of these. The explainer goes into them in more detail, but we think that beyond just the rate limiting to prevent multiple tokens from being, or too many tokens from being generated from the same, too many proofs from being generated from the same token, right? If a bot farm were to generate a single token, distribute it to all of the bots, and they were all to reuse it, right? Beyond the need to prevent that from happening, which is the rate limiting that Sam was talking about in the previous session, there probably needs to be some rate limiting on the usage of this API, even just on a given device, to make sure that, for example, you can't set a token on an arbitrary amount of domains and then generate proofs across them to be able to identify the user based on some unique pattern, right? So there have to be independent limits there. This is similar to other work that's ongoing in Chrome. So for private state token API, it's a similar concept, but there it's a single redemption model, right? You get the token, and then you redeem the token, and then that proves something about the context to be able to move forward. Here, because you're able to set this token and generate multiple proofs, there is a bit more, or there's more utility over time, and the token itself, as the previous example showed, can sort of mature into usefulness rather than having to be useful, the moment that it's sent over to the browser for storage. And it's also sort of similar in some aspects to things you can do with the shared storage API in that it's a gated API to be able to set first-party data and then access it in third-party contexts in sort of a limited way. And so in the future, the initial API we're proposing has a way to set an integer token, and then the proofs you generate compare that token against another integer you provide to see if it's less than or equal to the value in the token. But ideally, additional predicates would be supported, maybe additional types would be supported, other algorithms beyond the current BBS standard that Sam implemented. And there might be some benefit in having issuer fungibility, right? Right now, you have to have the same provider who issued the token and then is validating the proof at the end. There might be value in having a ring of issuers who could all generate tokens and then cross-validate against each other without having to share their individual private keys. And if you want to learn more about the private proof API, there's an explainer link here, and there's a white paper with more details on the cryptography. Okay, so I think we're ready for questions, but I'm also not entirely sure how they work in this venue, especially if Schoolhouse is muted.
Yeah, we still can't hear you, Schoolhouse.
We can see the chat, so if people like join the meet in companion mode and they send messages, we could see them there.
Yeah, or if somebody wants to pass around their computer or something.
Okay.
Oh, there you go.
There we go. Ah, cool. All right. Yes. So, any questions from the room? Okay, we got one over here.
Hi, Yoav, Vice Shopify. So you didn't say that explicitly, but I'm assuming the data is not partitioned. The proof that is being proven, the data that is being proven is not partitioned. Is that correct?
Yes, that's correct. The token goes into unpartitioned first-party data for that origin or that site, and then when proofs are generated against it, it's using that same token.
And if anybody's remote and wants to ask, just raise hand on the Meet API. Anyone else from the room? Okay, got one over here.
Yeah, I'm Sunny. Nice work. Just wanted to ask a bit about the range proof. Like, how does that work? Is it like cryptography that we want to understand, or something that you could talk about here?
It's cryptography that even I have trouble understanding, and I've implemented it. It uses a range. There's sort of two range proofs involved. So there's the range proof for the rate limiting, which uses a range proof that's based on essentially decomposing the number into a series of bits, and then proving that the sum of those bits, multiplied by the 2 to the I that belongs there, equals the number. And then you know that the number must be less than or equal to 2 to the I. That's what we use for rate limiting. And then we sort of modify it in a sort of subtle way that allows it to be used for an arbitrary rate limit instead of just 2 to the n. And then the other range proof is based on this much more complicated to explain thing called a 4-square range proof. And I don't even want to try, but you decompose the number into 4 squares, and then you do some magical stuff that I can't explain. I can direct you to the document on the screen here, though. In the range.pdf document, we do explain exactly how we're doing it, though we don't have a proof in there. The paper is called Sharp, if anyone's curious, like something short, relaxed proofs, approximate proofs. I forget what it stands for, but it's Sharp range proof. We'll get it for you.
There's one in chat. All right, there's a question in chat from Ishan. Will there be any limits on the type of challenges a site can request? Does allowing any challenge pose privacy concerns? And is this similar or an advancement over what Apple and Cloudflare built?
Yeah, this is a great question. I think that right now we're only allowing you to have a credential, which is a single number, and then you can request a proof that number is less than or equal to a given upper bound. And so that is the limit. Like, that's all we're deploying, or all we're proposing to deploy. And we don't necessarily have a concrete plan to move beyond that. However, there's a lot of different predicates that you would want to support for different use cases, and you could see going beyond that for a lot of different ways. There are practical privacy concerns where, for instance, somebody could put like an ID inside of there, and then they could do a binary search, right? They could use fingerprinting data and try to guess which ID's in there, and then do a binary search using the rate limit that they have access to. And they can sort of augment fingerprinting in this way. So there are risks of having arbitrary predicates. Those risks are mollified to some extent by reducing fingerprinting surfaces. That's kind of my thought process on it. Ari, do you have any thoughts on this?
Yeah, I think the reason that we're starting with this model with the rate limited range proof is because it seems like it would be sort of hard to abuse for the purpose of re-identifying the user. As it expands, we're definitely going to have to make sure that we don't build a series of blocks that can fit together in a way that enable malicious behavior.
All right, got another question from the room.
Hi. I'm Riley from Google. I'm curious how we sort of intend on explaining this to users, because maybe I missed it in the presentation, but like how this interacts with clearing storage. If like we clear storage, but it doesn't clear this storage, then we're not really clearing storage. And like I can imagine that just the presence of the proof, the site could behave differently, and then it's clear to users that we like didn't clear storage, and that will like immediately feel creepy. And so like I'm curious how this ends up turning into like user visible behavior.
I want to be super clear that when you delete your storage, we will delete these tokens from the browser.
Any follow up? So thumbs up.
I should note the exact mechanics of like, is it if you clear cookies, they go away, or if you clear like non-cookie storage, they go away. Like that part has to be figured out, but we don't want anything unexpected to happen. If the user believes they've reset, the reputation with some site, this definitely should be cleared as part of that.
Any other questions from the room?
I want to mention one last like potential future work, which wasn't in the last slide. That's essentially the ability to potentially be able to update the contents of the token, rendering the old token illegitimate, so that you could potentially have state that you sort of step through some state machine in there. That's a little bit more like research level, but that's something that I think solves a lot of uses that aren't solved by this current approach.
All right, it looks like we're done with questions then. Thank you very much, you two.